Hello everyone, and welcome to today's webinar. My name is Pat Hawkins. I'm a design engineer in the Thorlabs Advanced Photonics department, and I'll be moderating today's talk. Today's presentation is Fluoride Optical Fibers for the Mid-IR, and will be given by David Gardner. Dave has been with Thorlabs for 11 years and is currently working as a senior process engineer. Within this role, Dave leads the development and production of our fluoride fibers while also supporting the characterization, testing, and R&D for our silica and fluoride manufacturing teams. In this presentation, Dave will provide some history on fluoride fiber and glass R&D, as well as the current state of fluoride fiber technology, including that manufactured here at Thorlabs. We will explain how fibers drawn from this material, unlike traditional silica fibers, are able to transmit light ranging from the low visible to mid-infrared while maintaining robust mechanical strength. I've worked in the product development team at Thorlabs for about 10 years, during which time I've frequently worked with Dave on R&D projects, metrology, and introducing new fibers and accessories into the Thorlabs catalog. We're accepting questions throughout the entire webinar. To submit questions, just click on the Q&A button, and Dave will address those at the end of the talk. This talk will be uploaded to YouTube if you'd like to review and share, and on our website you'll also be able to sign up for our next webinar, which is on Wednesday, November 16th, titled Quantum Optomechanics at the Standard Quantum Limit, presented by Thomas Corbett, professor at Louisiana State University. Okay then, I'll turn it over to Dave now for fluoride fiber.
Thanks, Pat, for that introduction, and thanks to everyone who joined us today. I'm really excited to give this talk. Fluoride fibers are near and dear to me as I spend most of my job working on them. So we hope you like the presentation today. Hopefully my slides are going to show up here, and then we'll get going. All right, so starting off with an agenda for today, what are we going to talk about? First part of this talk is going to be some fundamentals of fluoride fiber, talking about these glass materials and what makes them special. The second section will be a little bit of a history of the R&D of fluoride glass and fibers through the years. And then finally, we'll close with a section kind of talking about, well, where are they at today? State of the art, what do we do here at Thorlabs and at other manufacturers? How good are fluoride fibers? But starting off in the beginning, the first section is about glass materials. So to talk about fluoride glass, let's first talk about what is a glass material in general. So glass is another name for it was a amorphous solid. And what that means basically is that the molecules that make up this material are oriented randomly in the material, as opposed to a crystalline material where there's some sort of repeating pattern, like we see hexagons here in this example. So yeah, glass is really any material where we have this amorphous structure. And we achieve that by what's called quenching the material, which means rapidly cooling the material from a liquid to a solid. And the idea here is that rapid cooling, quote unquote, freezes the material so it becomes a solid, but we don't give the molecules time or opportunity to rearrange into this crystalline solid material. What we're left with is kind of like a quasi-stable state. It's not the lowest energy state, which would be crystals, but we've kind of frozen this material in this, it's a stable state. We'd have to heat it to get back to a liquid to then form crystals. And it doesn't undergo like a phase transform where we have a discontinuity of like volume and energy and viscosity. This glass material, it's a smooth transition from liquid right into that amorphous solid. Not all materials are what we'd call glass formers. That's this concept of glass forming ability, which is what's the tendency of a material to form a glass rather than a crystalline material if we're cooling it, let's say, at a constant rate, so many degrees per second. So yeah, some materials won't form a glass, or it's very tricky to get them to form a glass. Other materials like polymers will only form like a glass material, amorphous material. There's no crystalline state. In the world, silicate glasses, which are based on silicon dioxide or silica, are definitely the most common. Not necessarily the topic of this talk per se, but I'm going to reference silica glass a lot as a reference point to compare to fluoride glass. Those are used in a lot of applications, from window glass, food packaging, all the way up to conventional fiber optics. So a very important property when we talk about glasses for optical fibers is that you can heat a glass material, and once you get past a certain temperature called the glass transition temperature, it'll begin to soften. So this is very different than a crystalline material. If you think of a crystal, it's a solid. As we heat it, think about ice, for instance. As we heat it, you have a sudden phase change where it goes from a solid to a liquid. Glass, on the other hand, if you're at low temperature, it's in this brittle, glassy state, which, again, stable over time. And then as we increase the temperature, we have a smooth transition into a more flexible material. It's been likened to taffy or honey, or you can choose your own food analogy there. But that's what we'd see in something like glass blowing. We see in the photo here. We have this soft material where it still holds its shape, but it's soft and workable. And this is very important for fiber optics, because this above the glass transition temperature, where we have this soft material, this is what allows a glass to be drawn into an optical fiber. You cannot draw a crystalline material into an optical fiber because it does not have this property. Okay, so with that short intro, let's talk about fluoride glass, the topic of this talk. So what is a fluoride glass? Basically, the idea here is these are true glass materials. They're true amorphous solids, and they're composed of heavy metal fluoride compounds. So as opposed to like SiO2 and silica glass, we're going to have fluorine instead of oxygen, and we're going to have a variety of metals in those molecules. Unlike most IR materials, IR optical materials, I have a list here. These are all crystals, CaF2, calcite, etc. Fluoride glasses are true glasses, true glassy materials instead. They are completely different chemistry, completely different constituents than our standard silica glasses, which would be SiO2 plus maybe some germanium oxide as dopants in fibers. And they're multi-component glasses, as we're going to see on the next slide. So whereas pure silica glass is pure silica, our fluoride glasses are multi-component glasses. So you have a few different heavy metal fluoride compounds making up these glasses. So here's, as an example, some fluoride glass families. So the idea here is, as I mentioned, different materials have different glass forming abilities. Some are stronger glass formers than others. We're working in this space where we have many different fluoride compounds to choose from. And through a lot of R&D, we've kind of honed in on a few, I'm going to call them glass families. So it's a group of compositions that occupy a relatively stable space, as if we were to graph out glass forming ability. You need a reasonable good glass former to be able to process these materials into an optical fiber without crystallizing or devitrification. And so, yeah, there's a few different glass families that are standard in the industry. Most famous being what we call ZBLAN, which is an acronym for zirconium fluoride, barium fluoride, lanthanum fluoride, aluminum fluoride, and sodium fluoride. The classic composition is in those percentages, so as you can see, the multi-component nature of the glass. And this is chosen because this combination and related compositions around there will give you good glass forming ability. This material will actually form a glass when it's quenched. So that's what we call the fluorozirconate glass family, or ZBLAN. There's also fluoroindate and fluoroilluminate glasses, which use different fluoride compounds. You can see some examples there. And these different glass families have different thermal and optical properties, pretty close, but slight differences. So like, for instance, this curve here is showing us transmission through a 10 millimeter thick piece of glass for ZBLAN and indium fluoride. I don't have a fluoroilluminate line on here, as we don't really work with those materials at Thorlabs, but that's going to be a bit shorter transmission cutoff. But they're compared to, let's say, a silica, UV fused silica glass piece at 10 millimeters, and you can see we get much better IR transmission. More on that in a moment. So with these glass families, the last part of our intro is, well, what is fluoride fiber? So the idea here basically is we take these fluoride glasses, we make a relatively standard step index core and cladding design, and we are able to draw these glass types into fiber. So this picture here on the top right is an actual microscope image of a cleaved end face of one of our fluoride fibers. This is a multimode fiber, so you can see the glass core, glass cladding, and then we have an acrylate coating. Very standard conventional fiber designs. Really, the designs aren't novel. It's all about these materials that makes fluoride fibers novel. And in addition to, we have novel properties with these materials, I'm going to say there's also novel manufacturing practices. These glasses they are weaker glass formers compared to silica glass. And that makes the manufacturing much more tricky. We'll get into that a lot in this presentation. But while we end up with a rather conventional optical fiber, the path to getting there and the manufacturing is pretty different. One more slide. What is fluoride fiber? So here we're going to talk about, in my mind, there's two big features that differentiate fluoride fiber from a standard silica-based fiber. Feature number one, which is, the big one, we have a transmission window in these fibers that extends much farther into the IR compared to silica glass. So you can see here, this is kind of a new version of that same graph we looked at. Now we're looking at optical fibers, attenuation in dBs per kilometer, and we're comparing silica multimode fiber to indium fluoride and Z-bland multimode fibers. And as you can see, well, attenuation isn't quite as low, more on that later, but we see transmission much further out into the IR, while preserving transmission in the visible and into the UV a little bit as well. So we get this nice broadband transmission from the UV to the mid-IR. Call it about 4 to 4.5 microns for Z-bland, depending on what loss you can handle, and for indium fluoride, out to 5 microns at least transmission. So that's the first big feature, and we're going to do a deep dive on that in a moment. Second big feature is if you have a rare earth doped fluoride fiber, we're going to see greatly reduced quenching of certain excitation states, which can open up some laser lines for different applications. So first, we're going to deep dive into bullet point 1, and then feature 2 we'll talk about after that. Okay, so next section. To understand this UV to IR transmission of fluoride fibers, what we want to look at is, well, how does it work when you have a glass, a transparent material? It doesn't have to be a glass, but a transparent material. How does it work that we transmit light through there? And really what that comes down to is intrinsic and extrinsic losses. Intrinsic would mean, how does the transmitting medium itself attenuate the light going through? And there's a few different mechanisms which we're going to look at. And then also there's extrinsic loss. Not going to talk about that in this section, but that would be, things that are outside the transmitting medium, or, inclusions, bubbles, crystals, impurities that are going to absorb everything else. But for the purposes of this deep dive, we're going to talk about the intrinsic losses. So again, how does that transmitting medium itself transmit the light? This is the general equation for looking at the intrinsic loss. We're going to express that in terms of dBs per kilometer, which is pretty common in the fiber optics world. So what's the loss over a certain unit length of fiber? And there's 3 parts of this equation. The first part is electronic absorption. Second part is due to Rayleigh scattering. And the third part is due to multiphonon absorption. And as you can see, they're all a function of the wavelength. So we're going to go through those one by one. First is electronic absorption in the UV. So I'm going to show you the same graph over the next few slides, and we're going to see these different effects. First one, electronic absorption. Basically, the idea here, we're talking about short wavelength photons or high energy photons, and as the wavelength gets short enough, you start to have the energy of the photon matching the band gap energy of electrons in this transmitting medium. All the different, energy levels, all the different orbitals of all the different constituents in this glass composition. So what we have is the photon energy matches this band gap. The photon is absorbed. Now we have an electron in an excited state, and that energy is eventually dispersed via non-radiative means. Usually the molecules are going to vibrate, so it turns into heat. We get a smooth curve because there's a lot of different energy levels, and this curve is very steep. So we see it increases sharply in the UV here. A note about this graph. So we're looking at wavelength on the x-axis, and we're looking at absorption on the y-axis. And this is a log scale of absorption. dBs are already a log scale, so this is like a log of a log scale. And just to put some round numbers on this, 0.01 dBs, so that would be like if you had a 1 kilometer long fiber with 0.01 dBs per kilometer, that's going to be 99.8% transmission. So effectively almost no loss over a kilometer. Move up to 1 dB per kilometer, that's 79.4% transmission through a kilometer. So, pretty good, but certainly there's some loss. If you go up to 100 dBs, that's now, ready for this? 1 times 10 to the minus 8% transmission, which I'm going to say over a kilometer, that's no transmission. If you have a short length of fiber, you can get some light out, but no transmission through a kilometer. So that's how quickly, what I'm trying to show here is how quickly this absorption increases. And again, this is the first part of that equation. We have lambda up here and the exponential, and we see steep curve. The next effect is Rayleigh scattering, also known as why the sky is blue. The idea here for Rayleigh scattering is it's inelastic scattering, elastic scattering of photons in a glass. Why this occurs is there are little spatial irregularities in the transmitting medium in the glass. So compositional fluctuations on a microscopic scale or density fluctuations on a microscopic scale. And these are all going to result in index of refraction fluctuations on a microscopic scale. So yeah, we're going to see, small irregularities in the material, and photons are going to be scattered by this, and it's much more severe with short energy or short wavelength, high energy photons. Typically what we talk about is the wavelength on the same order of magnitude as the size of these irregularities. So that in the equation is this constant b over lambda to the fourth. So decreases strongly with longer wavelength. And that's this red line here. There's also Brillouin scattering, which is inelastic scattering. It's present in glassy materials, but several orders of magnitude lower. Kind of works the same way. So we're not going to talk about that, aside to say that in a crystalline optical material, which we can't make into fiber, you don't have Rayleigh scattering. That crystal lattice means you don't have these density fluctuations. So Brillouin scattering is dominant in those materials. Okay, then last of three effects. Now we're going to talk about IR absorption, also known as multiphonon absorption. Notice I say phonon, not photon. The idea here is we have, certainly, especially as we get to longer wavelengths, we have longer wavelength photons, which means lower energy photons. And these can be absorbed. Now our photon energies start to match the energy of different vibrational modes in the different molecules that make up the glass, which we're trying to show by this cartoon here, which hopefully is playing okay. But there's all these different ways that molecules can stretch and bend and twist and so on and so forth. And again, this is all going to absorb photons, and then eventually these vibrations are going to just be dispersed as heat through the matrix. So we lose, we have photons turning into non-optical energy. So this effect actually increases with wavelength, as opposed to the other two, which decrease with wavelength. And again, we get a smooth curve because there's a lot of different vibrational modes. You can see we have two constants, upper and lowercase c, and then we have lambda up here in the equation. So we get this, this curve like the green line there that you see. So this equation for absorption is, of course, we're adding these effects together. And then the next slide, we're going to look at that. So we have, we can combine the UV, Rayleigh, and multiphonon absorptions. It's really just blue curve plus red curve plus green curve. And remember, we're on a log scale here. So when there's only kind of one curve dominant, the others are negligible effect. So what I'm going to do now is overlay a purple line, which is the total absorption. And there you have it. As you can see, it really rides these curves. Like right here, we have 10 dBs per kilometer from multiphonon and less than 0.01 from Rayleigh. So that's no contribution. Right here, you can see the loss is going to be a combination of Rayleigh scattering and this multiphonon absorption. That's going to be where the minimum absorption of the material is at that wavelength. So we can draw a line there. For this material, this is Zevaland glass, we have this minimum attenuation is around 2.5 microns. And that is purely dictated by where the location of these multiphonon and Rayleigh scattering curves are, where they intersect. Okay, so to wrap it all up, how do we get from, and that's a great theory, how does that turn into, well, fluoride fiber transmits in longer wavelengths than silica fiber? The key is this fluoride glass is much heavier than silica glass, much more dense, much more heavy molecules it's made up of. So silica glass, about 60 grams per mole of these SiO2 molecules. Fluoride glass, it's a multi-component glass, but if we do some weighted averaging, it's around 142 grams per mole, so more than double. And what happens here is, well, what we're showing here, this is for silica glass, the same curve, multiphonon absorption and Rayleigh scattering. If I overlay the fluoride curves, like that, what we see is, most notably, the green line is pushed to the right. So much more decreased, much less multiphonon absorption at a given wavelength. Or in other words, this multiphonon curve is pushed to the right, pushed to longer wavelengths. And that's because you have a heavier glass matrix, so you need lower energy photons to match those vibrational modes and be absorbed. The Rayleigh scattering may also decrease a little bit. There is some ambiguity in the constants for fluoride glasses, pretty hard to measure. So it's possible we get a little bit of increase, a little bit of help there too. But really, again, this intersection of the two curves is what's going to define this minimum attenuation. And you can see we're about an order of magnitude lower in the fluoride glasses than the silica glasses for minimum attenuation. And then, yeah, you get this whole transmission window here at these longer wavelengths, which you don't get in the silica glass. So in a nutshell, that's how fluoride glass transmits in the mid-IR where silica glass can't. In an optical fiber where you have long path lengths, this becomes very important. You see these long attenuation curves moving out into the mid-IR. Okay, second feature, which I mentioned, is this, well, we're dealing with doped glasses. Basically, the idea here is we can, this is a common thing in optical fibers, we can add some rare earth ions into the glass matrix. And these can do useful things like create a fiber laser or a fiber amplifier. And we call this an active fiber. So the fiber can become, for instance, the medium where the light oscillates to form a laser cavity. In silica glass, this is used in a lot of applications, most notably EDFAs, erbium doped fiber amplifiers, which are used all over the telecom world. In fluoride glasses, we have this heavier glass matrix. And the idea there is if we have one of these rare earth ions, it's now absorbs a photon, it's in an excited state. It's harder for it to give that energy to the glass matrix because, again, we have that reduced multiphonon absorption. That means this molecule is going to stay in its excited state longer, so the excitation lifetime gets longer. And that makes it much easier to achieve population inversion, where we have, majority of these molecules are in the excited state, and hence you can have a fiber laser or fiber amplifier. So because we have this reduced quenching, there are some laser lines that are inaccessible or too strongly quenched to use in silica glass, but they can be used in fluoride glass. In this table here lists a few different examples, most notably like praseodymium at 1.3 microns can be used for an O-band telecom amplifier, like a 1310 fiber amplifier, which you can't do with praseodymium-doped silica fiber. Of course, there are many where silica glass just doesn't transmit either. Okay, so we've gone through the two big features of fluoride glass. I'm going to spend just a moment here talking about the other properties of the glass. What's it like to work with? Optically, this maybe is a pretty convenient feature too. The silica glass and fluoride glass are pretty close in refractive index. So the gray curve here is silica, and then we have Z-bland and indium, our two fiber families here at Thorlabs. You can see we're, 1.45 for the silica, 1.5 for the fluoride. Close enough that you get similar Fresnel reflections, around 4%. And if you splice these fibers, you don't have a huge loss at that fiber-to-fiber junction. Dispersion is also similar, so the change in refractive index with wavelength. Interestingly, the change of refractive index with temperature, dN dt, is negative, which is opposite of how silica glass works. Mechanically, fluoride glasses, they're softer than silica glass. I've heard them called soft glasses, actually, in certain contexts. Higher density, which we already mentioned. Lower theoretical tensile strength, which comes into play with fiber strength. Thermal properties are very important. A much lower glass transition temperature. So from earlier in the talk, that's where we're looking at how does this material soften with temperature. So silica glass, pure silica glass, you're going to be over 1200 C, perhaps even a lot higher. Soda lime glass is maybe 700 C, 600 C, something like that. Fluoride glass, we're down under 300 C, where this glass is going to soften. So that means we're going to cast glass, quench glass, draw fibers at a much lower temperature. Viscosity also changes quickly with temperature, much more quickly than silica glass. You can see that this curve here on this graph, viscosity versus temperature. Poor thermal conductivity compared to silica glass, and also just speaking about the glass forming abilities, this glass will crystallize instead of forming a glass if we don't quench it fast enough. You need to go, theoretical limit's probably about 0.2 degrees C per second, really 1 degree C per second. And these are for the most stable compositions. That's what you need to be able to achieve. Poor thermal conductivity makes it hard to get the center of a glass piece to cool quickly. So these two features together limit what volume of glass we can quench successfully. And finally, chemically, we have a little bit of decreased chemical resistance compared to silica glass. Silica glass is very chemical resistant. Fluoride glasses in liquid water, they can be attacked slowly, not water vapor, but if they're immersed in liquid water, and also some acids can attack them. All right, so that's basically the end of part one. I've told you about, intro to fluoride glasses. I'm going to do a quick aside pretty quickly. It is worth mentioning, well, are there other true glass materials that work in the mid-IR? And there are two that I thought were worth touching on. The first is the chalcogenide glasses. Those use, the constituents are chalcogens, sulfur, selenium, tellurium, technically polonium, but that's not used. And pretty cool image I found here of some chalcogenide glass samples. Interestingly, they transmit further into the mid-IR, but they don't transmit in the UV and the visible. That's why they look opaque in this visible light image. But you can get out to 10 microns in a fiber, which is impressive. They are, in addition to being opaque in the visible, we have a very high index of refraction, so you get like 20% Fresnel reflections without an AR coating. And they're, materials are pretty toxic, but certainly they're useful far out into the mid-IR. And on the other side of the spectrum, the germanate glasses, so a germanium oxide fiber, pretty similar to silica glass, but they can transmit out to about 3 microns, whereas in silica fibers, you only get out a little over 2 microns. Here's a comparison, just the same attenuation curves we looked at, but we've added the germania and the chalcogenide glasses. I think we mentioned this in the intro. I know I'm going through these curves fast, but we will have these slides up for review later in this recording of this webinar if you want to, look at some of these in more detail. Noteworthy here, yeah, the chalcogenides extend much further out, but the baseline losses are even higher than the fluoride glasses and the silica glass. Okay, so that's part one of the talk. Part two, now we're going to talk about the history of fluoride glass and fiber. Where did it come from? What sort of R&D has been done? So fluoride glass was first fabricated in 1974 in France at a university. Interestingly, like a lot of discoveries in science, it was an accident. So the researchers were investigating complex fluoride crystals, and they quenched the material and saw, wow, this formed a glass, not a crystal. And that was a great discovery. The original glass was zirconium fluoride, barium fluoride, sodium fluoride. And then they were able to add some neodymium fluoride, which is a rare earth dopant, and they were able to observe the reduced quenching of the 4F32 level on the neodymium 3+ ion. And that was the big clue. Look, wow, the multiphonon absorption is going to be decreased in this glass. It looks like it could transmit into the IR. So this, I have a little screenshot here of the first paper. And basically, this is the first three main bullet points are the first paper. Eventually, more research, the Z-bland composition was arrived at, where we have that zirconium, barium, sodium composition. We added lanthanum and stabilizer, and aluminum as well. Well, sorry, the lanthanum is a lanthanide you can replace neodymium with, and the aluminum was the, help the glass forming abilities. And there's many other, we like to use these acronyms, many other glass compositions that have been studied in the Z-bland extended family, let's say, and then the fluoroaluminate and fluoroindate glasses as well. Z-bland, there's a lot of papers in the literature from the 1980s. Basically, the idea was, we figured out that there's this decreased multiphonon absorption. We figured out that there's this potentially very low minimum attenuation, much lower than silica fibers by an order of magnitude. And so a lot of telecom organizations were researching Z-bland fiber. Can we use this for long-haul telecom and not have to use amplifiers in our long-haul systems, or not as many? The R&D goals were really to try to approach that theoretical minimum attenuation, as well as making a fiber that's mechanically robust. You can bend it without breaking. We can have good control of the fiber geometry and things like that. A lot of research in the 80s, early 90s. Unfortunately, so far we have not been able to reproduce that low theoretical absorption in an optical fiber. We have no reason to believe that the numbers are off. Really what it is, we can't make a fiber so far that achieves that theoretical minimum loss. So what you can see here, this dark blue line is about the best Z-bland attenuation curve I could find, around 1 dB per kilometer. And we still have, call it 2 orders of magnitude to go of improvements. And why is that? Well, earlier we talked about intrinsic loss, which we went over, and extrinsic loss. Turns out extrinsic loss so far is dominant. So it's not that the glass isn't good enough, so to speak. It's that, hard to get rid of impurity absorptions, inclusions in the glass, in the fiber, et cetera, et cetera. So extrinsic loss remains dominant in fluoride fibers. One more comparison there. So again, we looked at this curve earlier. Here's silica versus Z-bland glass, theoretical attenuation. The first curve I'm going to overlay, a gray line. This is Corning SMF28, which is like the industry standard telecom fiber. This is an attenuation measurement we did here at Thorlabs. So this is a real fiber attenuation curve. This region here is where it's single mode. And you can see we get very close to the theoretical minimum attenuation. The minimum is maybe around 0.12, and we're at 0.17. And this is just a run-of-the-mill, off-the-shelf fiber. This is nobody's hero run. This is what we can do on a regular basis in silica fiber. Next, I'll overlay that Z-bland curve, so you can see where Z-bland's about an order of magnitude attenuation behind silica fibers. We're at 1 dB per kilometer, and we have not approached the theoretical minimum yet. So, and really what this is fluoride technology is less mature. We think that this is possible. It's just we have to get there yet. As fluoride researchers, this is what motivates us. So one last comment on the history of fluoride fiber R&D. Like I mentioned, the big impetus was, can we use Z-blend fibers for long-haul telecom? This low theoretical attenuation could be super useful. We could have long fiber runs with almost no loss. That hasn't happened. The industry has really settled on silica fibers with EDFAs, and those work great. And really, several factors, and I thought that was worth going over because Z-blend for telecom comes up a lot. And we don't really think that it's going to take over the long haul market. So attenuation, as we mentioned, we haven't achieved that theoretical minimum. We haven't beat silica fiber in attenuation yet. Mechanical durability. So historically, fluoride fibers were very weak. It was hard to break them without bending, or hard to break them when bending them, due to extrinsic defects. In addition, the theoretical maximum strength is lower as well. Very tricky to work with, very tricky to manufacture, especially consistent fiber in long lengths. Things like that fast viscosity change with temperature makes them hard to work with. As I mentioned, you can only make about a 25 millimeter thick piece of glass. That's the theoretical max. In practice, we're usually working with preforms about 12 millimeters in diameter. And that's due to how fast you have to quench the glass to not have it form a crystal, combined with the glass is pretty bad at thermal conductivity, so it's hard to get the heat out of the middle of the glass piece. So if you run all those numbers, 25 millimeters is about the theoretical max. So yeah, hard to make large preforms like you have in the silica world that can make long lengths of fiber. So there's a economic angle there. It's important to note that the Z-blend theoretical minimum is at 2.5 microns. That's a wavelength out in the mid-IR. Anybody who does photonics in the mid-IR knows that all of the equipment is not as good as invisible and in the IR. Those longer energy or longer wavelength, low energy photons are hard to work with. So hard to get fast detectors, lasers, modulators, things like that. So for these reasons, the industry, like I mentioned, is really settled on silica fibers plus EDFAs, very mature technology. And yeah, a little bit of a failure for fluoride fibers. The big research topic was long-haul telecom, and they have not achieved that. So we end the second part of the talk on a bit of a downer. The history of fluoride glass R&D. It didn't work for what we thought it would work for. But all is not lost. So the third part of the talk is going to be about where is fluoride fiber today? How has it improved since quote unquote back in the day? So fluoride fiber today. We have a lot of niche applications that fluoride fiber has moved into. We're not doing the long haul telecom, but there are a lot of applications where fluoride fiber is advantageous. Even though we don't have ultra low loss like silica fibers or like what fluoride is capable of, if you're using the fiber in shorter lengths, these losses can be negligible. 1 dB per kilometer, for instance, is 80% transmission over a kilometer. That's 0.001 dBs per meter, basically nothing. Anyway, so a lot of great applications. Anything where we need mid-IR transmission, first and foremost, because these fibers transmit from the UV to the mid-IR. A lot of interesting fiber lasers and amplifiers. Here at Thorlabs, we sell an O-band amplifier, actually based on our in-house praseodymium doped Z-blend fiber. Sensing and spectroscopy, a lot of interesting science that happens in the mid-IR, things like gas detection. Medical lasers are a big one where we have lasers around 2.7 or 2.9 microns where there's water absorption. Fluoride fiber can be a great power delivery fiber. Supercontinuum generation is a big one. Another interesting product we have here at Thorlabs is a mid-IR supercontinuum laser made with our indium fluoride single mode fiber, taking advantage of its nonlinear properties and its mid-IR transmission. So a lot of interesting applications, a lot of interesting science in the mid-IR. Looking at the market today, certainly, fluoride fibers are a niche specialty fiber. But they are available commercially. 3 manufacturers, including us, Thorlabs. We manufacture here in Newton, New Jersey in the United States, which is where I'm talking to you from. In addition, there are manufacturers in France and Japan, and some universities as well, who do fluoride fiber R&D and have draw towers and can make their own fluoride fibers. And really, the offerings from the industry for fluoride fibers cover all the sort of standard fiber designs: step index, multi-mode, single mode, dual clad multi-mode for high power, rare earth dope fibers, in addition, fiber cables, fiber devices, things like that. So here at Thorlabs, fluoride fiber is a big focus of our R&D, and we've been working for years to improve fluoride fibers, as have our colleagues at other organizations. And really, the goals for fluoride fiber R&D is let's improve the attenuation first and foremost. We got to get rid of those extrinsic defects so we can get close to that theoretical minimum attenuation. In addition, there's other characteristics that matter in an optical fiber. So mechanical robustness: can you handle the fiber? Can you bend the fiber? Can you build it into a device without it breaking? That's very important. Can you actually manufacture this fiber in volume, long continuous lengths? Can you control things like the fiber geometry, core size, cladding size? So these are all things we're working on in really to close the gap to silica fibers. I mean, their performance is the benchmark, so we want to get as close as possible. And yeah, you can see here, this graph just shows at Thorlabs, we've been doing fluoride fibers for a little under 10 years, and we've had some nice improvements. What we're showing here is not a hero run, but actually just our average attenuation for all of our fiber runs in a year. And you can see how we've improved year over year the performance of the fiber, and it continues to improve. So yeah, in my mind, fluoride fibers have improved greatly from the early days, both in performance and manufacturability. Next couple slides, we're going to go through a few challenges and solutions in general, or specifically, I should say, for fluoride fibers. So basically, this will be structured, this format of the talk will be like a slide, that talks about the problem, and then a slide that talks about one or more problems, and then we'll talk about, as fluoride fiber manufacturers, how do we solve that? So the first thing that comes up in optical fibers is impurities. We have this nice glass material which transmits into the mid-IR, but it turns out it's you always have some impurities in every material. And in an optical fiber, you're looking through many, many meters of glass. I've likened it to like a window that's 100 meters thick of solid glass. When you have a long path length like that, impurities are very important. Even things in like the parts per billion level still matter. So this curve here, this graph, we're looking at some of the usual culprits for impurities that absorb light. Well, transition metals are hard to keep out of the materials, rare earth materials, and then also water. That OH bond really loves to absorb. So we're looking at chromium, copper, iron, and nickel here, which are, some common absorbers, and you can see how they absorb as a function of wavelength. Now, to illustrate that point about it really matters in optical fiber, I want you to first look at the right y-axis scale. So this is in units of optical density per centimeter per part per million. So the idea is optical density is like how we specify neutral density filters. And if you have 1 part per million, you're going to get an optical density through a 1 centimeter thick piece of glass of basically nothing, 0.01. However, on the left y-axis, this is now talking in dVs per kilometer, so the fiber metric per ppm. And you can see even, the first line is 100 dVs per kilometer, which was that 10 to the minus 8th% transmission. So it doesn't matter in bulk optics, free space optics, but it matters in fiber with these impurities. Even 1 ppm of any of these is way too much. In silica fiber manufacturing, again, more mature technology, we can use vapor deposition, which gets us to like less than 1 part per billion. Fluoride materials, we have to use other means to purify, certainly an active area of research. So yeah, we're doing our best to try to reduce these impurities, and we have had great success. That's the first challenge for, how do we achieve low loss in the fibers. Second challenge is crystals in the fluoride fiber. And I've mentioned this a few times already, but basically this devitrification is an issue where we get crystals inside our glass matrix. And I thought this was a good image. This is a microscope image of a cleaved fluoride fiber, and we can see a crystal in the core warping the waveguide, and also we're going to block some of the light in the core and scatter it. So these point defects are an issue. This is a big contributor to that extrinsic attenuation. So what's our solution? What's our state of the art? We've been able to have great strides, improving both purity of the raw materials, so getting rid of those impurities, but also eliminating these crystals and other point defects. Here's another microscope image. This is of a fluoride glass rod, kind of a cross section. So in the first one, you can see this devitrification, these crystals that form in the glass. Whereas in the second image, we can see glass. So there's a few vacuum bubbles, but other than that, crystal clear, no pun intended, glass, which is going to have a lot less scattering centers. So this attenuation curve on the left, this is a recent improvement at Thorlabs. You can see the fiber attenuation dropped kind of across the board. That's due to the reduction in scattering centers in these crystals. And we also were able to remove this absorption peak. This is due to water, around 2.9 microns. And you can see in the lower curve, we don't have that. So these are the sort of improvements we can see as we refine our materials and processes. And this sort of improvement in the optical performance we've had here at Thorlabs, fibers that have shown great power handling over time. Our supercontinuum source, for instance, is a very high brightness source. We have a really, really high peak power in that glass. And we see low attenuation, but also no defects that are going to cause the fiber to blow up under high power. We have a lot of, like I said, fibers in the field that have kind of validated this performance. Okay, so next kind of challenge is mechanical durability. So what good is a fluoride fiber if you can't bend it without it breaking? We're at a little bit of a disadvantage here because the theoretical max tensile strength, which is kind of like the force required to break the atomic bonds along a plane in this material, it's lower in fluoride glass just due to the chemistry of the glass compared to silica, maybe a factor of 1/6. But then more dominantly, well, if we have any defects on the surface of the fiber, that's also going to decrease the mechanical strength. Chemical durability is also important. We need to, well, silica is very inert and fluoride isn't, kind of already went over that. But, these all kind of conspire to make it, we really need to have a perfect surface on this fiber so we can approach this theoretical max tensile strength so we can have a strong fiber. This next slide, same topic. So we're just looking here at a fiber break. So this is like we broke a fiber, or the fiber broke, and we looked at the end face on a microscope. You can see this fracture pattern, which is characteristic when fibers break. And you can see that nucleation site is a surface crystal. This is the coating of the fiber, this outer layer, and then the glass fibers on the inside here. And you can see this, this surface crystal. That's due to, again, devitrification, due to improper processing of the fiber during drawing. So this is going to decrease our mechanical strength. So with that challenge, well, what's state of the art? What's the solution? So these days, we can do, we've done a lot to try to get improvements to this mechanical durability of the fiber. We've come a long way in eliminating those surface crystals, maintaining that pristine outer glass surface, which if you've watched one of my previous talks, shameless plug here, but we have a talk on fiber manufacturing, and we talk a lot about why that surface needs to be pristine to maintain the fiber strength. So yeah, we've done a lot to remove those surface crystals. We can proof test the fibers now, which verifies a certain strength level along the whole length of the spool. We can also do things like a dual acrylate coating, which is the industry standard for single mode fibers, where we have a soft inner coating and a hard outer coating, which really improves handleability outside of just that tensile strength. And we really believe our fibers have come a long way in terms of mechanical performance, which is essential for being able to use these fibers in real world applications. So we'll take a break from the slides real quick. We have a little video. So this is just an example of how durable fluoride fibers are these days. You can wrap them around your finger. You can bend them to a very small loop radius, and this is a thing you can do reliably without breaking the fiber. So we're very proud of these improvements we've made throughout the years. So the last section of sort of challenges and solutions I'm going to talk about is manufacturability. Again, fluoride glass, we have that small working temperature range above the glass transition temperature, but before crystallization and at the right viscosity and all that. So it's very hard to make fluoride fibers in long lengths and in consistent, let's say, geometry control, all these specifications all in the length of the fiber. This has been a challenge throughout the years. Again, just due to the tricky nature of fluoride glasses when we're processing them into fiber. And we've had a lot of success here as well. So we've been able now to, we have the geometry of control of these fibers almost on par with silica fibers. You can see here a test report where we're looking at things like the concentricity of the core to a cladding in a single mode fiber, and also how well can we control the core and the clad diameter. So we've come a long way there, where we're almost at the level of silica fibers. We have full QC for all of our different specs we care about, attenuation, mechanical strength, geometry, all that. And really the take-home message here is at Thorlabs, we can really manufacture many kilometers of uniform fiber. We're ready, to manufacture fluoride fiber in volume if an application demands it. And that's, I think, something pretty new in the world of fluoride fiber, to have manufacturing control on par with silica fiber. So with that, one more video. We saved these to the end of the talk, but hopefully they're good. So this is just a little snippet of our fluoride draw tower, one of our engineers working on it. So you can see, what does it look like to manufacture fluoride fiber? Very similar to the draw process for silica fiber, which you may have seen in our previous webinar. We also have a video on our fluoride fiber webpage, another little shameless plug, but we made a video talking about our specific manufacturing capabilities, which I would encourage you to check out after the talk. I think it's in the links that we have as well. So we'll let this play through, and then we'll go back to last two slides. Okay, back to my slide deck. Hopefully it'll show up for everyone for just our last little bit of info. So just to close out the talk, I put together some tables, and my goal here was just to compare. I mentioned our goal is how do we get fluoride fibers to be as good as silica fibers? That's the benchmark. So yeah, this is a table. I'm not going to go through this in detail. This will be available online after if you want to look through. But really, you can see fluoride fiber, of course, wins the transmission wavelength. Silica fiber wins on attenuation. And also notably, we can proof test at a higher level. And this one is for single mode fibers. Maybe this is the most important one of all. Fluoride fiber, we're at about 100 meters continuous lengths we can manufacture, and silica fiber, we can do 63 kilometers, which is of course a lot longer. I should mention this comparison is for Thorlabs fluoride fibers. The other manufacturers may have slightly different specs they're at, optimized a little bit differently, but I think this is representative of, fluoride versus silica. So anyway, this is single mode fiber, and then one more slide, an analogous table, multi-mode fibers. And actually, these are both manufactured at Thorlabs. The last slide was Corning's SMF28. Here we're looking at 100 micron indium fluoride multi-mode fiber compared with a 105 micron core silica multi-mode fiber. Again, fluoride fiber wins the transmission range, wavelength range, and the silica fiber wins on attenuation and on max continuous lengths. Okay, so thank you all for listening. At this point, I want to open it up to some questions.
Thanks, Dave. Yeah, we have quite a lot of questions, so let's get to it. So you touched on this a little bit, but you had someone wondering, how big is the worldwide market for these types of fibers?
In a nutshell, much smaller than silica fibers at the moment. I don't have a good number on me, but the way I like to characterize it is, if you look at the fiber optic market for the whole world, I would say 80 to 90% are going to be telecom fibers, long haul and short haul telecom. And then that small other group is going to be our specialty fibers. Things like we manufacture here at Thorlabs, our silica multimode fibers, single mode fibers at different wavelength ranges, things like that. So that's our specialty world. And then I'd say fluoride fibers are some sort of like specialty of the specialty. So a tiny, tiny share of that specialty fiber market, maybe another factor of 10 smaller, these exotic fibers. So yeah, it's probably the best I can answer that question.
Okay, thanks. Um, we had a couple of questions about this actually. So I guess a few people out there are aware of our Made in Space program.
Yeah.
Could we talk about that a little bit? What are current activities, any successes? Did microgravity help in defect reduction? And yeah, if you could develop that a little.
Sure. So yeah, that's an idea that's been floating around for a while. Is can you manufacture Z-blend fiber in space? And it comes back to some work done, I guess, in the 90s. And the idea was that there's some sort of gravity-induced de-vitrification, so that that the different molecules weigh different amounts, and we're gonna have compositional fluctuations in our glass that zero G could solve. Really, we don't think that's viable. Both from the sense of, the idea there is we're going to make Z-band fiber hit its theoretical minimum, and we're going to sell it for long-haul telecom, which, if we had this slide where I think that's not the future of Z-band. In addition, we've not really seen any gravity-induced devitrification. We're able to make glass here at Thorlabs that's uniform, not devitrified, kind of uniformly through the whole piece of glass. So yeah, that's something that we're not super keen on. Certainly, never say never, but yeah, both from like a manufacturability standpoint and the idea behind it, the theory, and then thirdly the market. Yeah, not sure how much future there is there.
Gotcha. A couple questions about single mode fiber. So you touched on how we reduce attenuation for multi-mode fiber. Does that apply to single mode fiber as well?
Yeah, so all of the different, attenuation improvements, eliminating the extrinsic defects, those are important for multi-mode fiber, and I would argue they're even more important for single-mode fiber, where you have a much smaller core diameter. It's going to be much more sensitive to things like crystal sitting inside the core. It can be equally sensitive to things like absorption from impurities. So yeah, all of the improvements are really applicable to multimode and single mode fibers. With maybe even,
Okay.
You could say there's a few that are even more applicable to single mode fibers, like that dual acrylate coating I mentioned is a big one for single mode fibers.
Yeah.
It helps them function better.
Yeah, so someone noticed that, well, this is true for our single mode fibers. So the single mode cutoff wavelength is higher than the near IR because we designed them to function in the mid IR. But
Yeah.
would it be possible to have the single mode operation in the lower end of the spectrum? Near IR use, maybe even visible?
Yeah, definitely. And I would, again, a little shameless plug, I would refer the viewer to our single mode webinars where we talk about how you design a single mode fiber for a certain wavelength range. There's nothing that prevents fluoride fibers from having, let's say, a smaller core or a lower NA, which is going to shift that cutoff wavelength to shorter wavelengths, and you can get, a single mode fiber, in the near IR, in the visible. Maybe even like if you increase the NA, you can get a bigger single mode bandwidth between the cutoff wavelength and the bend edge. So yeah, no, there's nothing fundamental that they have to be in the near IR or in the mid IR. It's just, as you mentioned, our catalog fibers, we have a Z-blend and this indium single mode, and those cutoff wavelengths are chosen so that you get transmission from that cutoff all the way to the materials limit, the multi-phonon edge. So like the Z-band fiber is a 2.3 micron cutoff. That's right where silica stops transmitting, silica fiber goes up to 3.6, which is about where, or 4 microns, which is right about where the material stops transmitting. And then the indium fiber starts at 3.2 microns, and that's chosen so that it will transmit out right to about 4.6 or 5 microns, which is the material cutoff of indium. But that's just our catalog offerings. We can do many other designs.
Right. This is pretty important for usability. So how does stripping, cleaving, etc. work? Can you use the same standard tools?
Yeah, great question. So we're actually working right now on some documentation and some products for our website that are going to, be tailored towards how do you work with fluoride fibers. So I think there's a nice write-up coming. But for now, what I can say is stripping the fibers. First, I'll go with. We typically recommend chemically stripping these fibers or thermally stripping. You don't want to just use a mechanical scraper like silica fibers because they are a bit more fragile. Once you get the hang of it, it's pretty easy to do. Cleaving, we recommend, well, we have cleave recipes available for our Vitrain cleavers that we sell, and there are some more simple cleavers on the market that we can also recommend for 125 micron silica fibers. Yeah, and then termination, the fluoride fibers can be built into patch cables similar to silica fibers. So yeah, really, there's some details that are different, but they can be worked with in a similar way to silica fibers. And if there's specific questions on that, we're always willing to help our customers figure out how to work with fluoride fibers.
Gotcha. This is kind of an interesting question. So, this is an active area of research. How quickly can, advances in academia be incorporated into manufacturing? Do we have any examples of that here? Yeah.
I don't think I have a great answer to that question. I don't think we have an example of that. But yeah, certainly there are some university groups doing some great research. There's some conferences that have some workshops and different things on IR fibers. So yeah, there's there's definitely some opportunities for collaboration there, for advancements in the field.
I thought this was a good question. So, this was all about fluoride fiber, but CAF2 and magnesium fluoride also have great transmission, right? And that's what's typically used in optics. So why are we talking about Z-band and indium fluoride? Is it possible to make CAF2 fiber?
Yeah, great question. So that basically, I would refer us back to the very beginning of the talk where we talked about amorphous solid glass materials. And you have that, glass transition temperature. They get soft. You can draw them into fibers. So CAF2, magnesium fluoride, those are crystalline optical materials. Those are not glass materials. And so those, you cannot draw those into fiber. They don't soften. When you get them hot, they're going to go from a solid state, have a phase change into a liquid state, kind of more conventional way of working. And there is some research on like sapphire optical fibers, quote unquote. They've been done, but really it's not drawing a fiber. It's like growing a crystalline fiber structure. And maybe they can make them a meter long or so, or a few meters. So no, those materials are not viable for optical fibers. Fluoride glass is one of the only ones, and that's what makes it special. Fluoride glass, and I did include the chalcogenide glasses as well, as they're true amorphous solid materials, so you can draw them into optical fibers, and that's their big advantage.
Okay, so we have time for just one more question. So do you see a path forward for integrating fluoride fiber into components, amplifiers, splice devices, etc.?
Yeah, absolutely. So that's an active area for us. I mentioned earlier in the talk we have an O-band amplifier on the market. So that is a fluoride fiber integrated into a fiber amplifier. You can imagine things like a grating in the fiber, a doped fiber spliced to a passive fiber. You can make an all fiber, fiber amplifier or something like that. Yeah, these are all things that we think are, are pretty doable. Fluoride fibers can be spliced to each other or to silica fibers, fusion spliced, that is. And yeah, so we see, great potential for fluoride fiber in devices. As I mentioned, I don't think fluoride fiber is going to take over the long-haul telecom world. But yes, the fiber devices is really where I think, most of those applications I mentioned can be, great opportunities. And I think fiber amplifiers and taking advantage of not just the mid-IR transmission, but the reduced quenching of those laser lines, that's a really big one, moving forward.
Gotcha. Okay, I think that's about all we have time for. So thanks, Dave. Thanks to everyone for logging on to the webinar and checking out our talk. This will be on YouTube if you want to share it or reference anything in the future. And just remember that next week on Wednesday, November 16th, we have another talk coming on quantum optomechanics. So thanks, everyone, and hope you enjoy your day.